Hello, and welcome to the talk on the art gallery problem, the first approximation algorithm. I'm Tamar Mulso, or just Till, and this is joint work with Edouard Bonnet. Here you can see Edouard. And we are both in Budapest, in Hungary, at the Institute MTA Stucky, which is part of the Hungarian Academy of Science, or in English, Institute for Computer Science and Control. Okay, let me tell you about the art gallery problem. So it was introduced originally by Victor Klee in 1973, and he asked how many guards are needed to cover a polygon with n vertices. So here's a polygon, simple polygon with n vertices. This might be a guard, and he would or she would cover this region. Another guard covering this region, and so on and so forth. And now we have here 6 guards, and they cover the whole polygon. But actually, 4 guards would only be needed to cover this polygon. You can see that 4 guards are necessary because no 2 of these positions here can be seen by one single guard, so you need at least 4 guards. So that would be, for this polygon, 4 would be the right answer. And you could ask this question, can you interpret this question as an algorithmic question? You could interpret this question as a combinatorial question. But also you can interpret this question as what kind of polygons you have, and so on and so forth. For the talk here, we will talk about only simple polygons, and we will consider this so-called point guard variant or interior guard variant, where the guards can be anywhere inside the polygon or in the boundary or the vertex. This is in contrast to the more popular variant vertex guard, where you're only allowed to place your guards at the vertices. We think this point guard variant is more natural because you want to place as few guards as possible, and why restricting to the vertices? There's no reason. You could just add a vertex anywhere and it doesn't change the shape of the polygon, but suddenly have one more vertex. This vertex guard variant and many other variants of this problem are much more studied, and the point guard variant is almost not studied at all. So therefore, we really think this is the first approximation algorithm for this point guard variant for simple polygons. And and this is our main theorem. It works in randomized polynomial time, polynomial in the size of the input. And it has 2 mild assumptions. The first one is that these vertices are represented by integers in binary. You could also ask rationals, it's the same, but real numbers would not work for us. But we think it's realistic because computers work with integers and not with infinite precision, but only with finite precision. And then we also have this general position assumption, which more or less says no 3 extensions meet in a point. So what is an extension? So given 2 vertices, this orange line here would be an extension. So for any 2 vertices we have an extension, and we don't want that 3 of those extensions meet in a single point. This is our assumption, and if you wiggle a little bit, then these 3 would not meet in one point anymore. So it's also fair to call it general position assumption. Okay, so let's go through some related work. So the first is by Micha Sharier. So he says, okay, the point guard variant you can solve in this time, which is polynomial for fixed number of guards. So k is the number of guards, n is the number of vertices. And you can also call it an XP algorithm. And this is an observation because he just formulates a point guard problem as a first order formula over the reals, and then he uses algebraic hammer. So let's see how he does this. So if you have a guard, you can represent it by 2 variables, and if you want to ask is the guard inside the polygon, you can ask is it one of the triangles, and triangle containment is an algebraic test. Visibility, can this point see this point, is also an algebraic test. You ask is this segment crossing one of the other segments. And then the whole formula looks like this. Does exist G1 to Gk such that for every point, if the point is inside, then it's seen by one of the Gi. And then, okay, you apply the theorem. So when you know this theorem, it's very simple. If you don't know it, I think so apparently no one knows how to do it, and maybe you don't really want to use this because it's this black box theorem. Maybe you could do better, but no one knows except for k equals 2 someone, Patrice Belleville something, but this is already complicated enough. It seems not really a very feasible approach, but maybe people come up with new ideas. But then regarding approximation, there are two algorithms which I want to tell you about. So this is the first is a pseudopolynomial time algorithm, which is an approximation algorithm. It's by Deshpande, Kim, Domain, and Sharma. Couldn't find a picture of Kim. And pseudopolynomial means it doesn't run in polynomial time inside of the input. So what their idea? They just generate this huge point cloud, and then they use a set cover algorithm for this restricted to this huge point cloud. And the idea is, why should this give a good solution? They say, if I have an optimal solution, well, let's look at these 3 points around it in their dense points cloud. Then they think that these 3 points around it see whatever X would see. And I call this local visibility containment property. So the optimum of these dots would be at most 3 times the actual optimum. But it turns out this approach is wrong. It cannot work. We give a counterexample and explain why this is not working. The other algorithm is by Efrat and Harpalet. Here's Efrat, here's Harpalet, and their algorithm runs in polynomial time. It is an approximation algorithm, but I call it here heuristic because it doesn't give approximation guarantees in terms of the actual optimal solution. Their idea is to use a grid, but they don't store it explicitly. And because they don't store it explicitly, they can stay in polynomial time. And then they use some data structure to be able to randomly choose grid points, where they give different regions different weight. But as I already said, they have no proof of approximation. And again, they use this set cover algorithm. But the set cover algorithm actually just says, give me a random point. So what's the story here? So if their solution is S, and they know S is upper bounded by log opt grid times opt grid. So this is a log opt grid approximation algorithm. So their solution is at most log opt grid away from the optimal opt grid. So opt grid is just what would be the optimum if I were restricted to the grid. But what they don't know is, what about opt grid and the actual optimum? Is there a relation? So the actual optimum is you can't place your guard anyway, where opt grid is the optimal solution when restricted to the grid. So they don't know anything about this relation, so that might be that their solution S is arbitrarily far away from opt. So and that's the algorithm that exists. But they say it's likely that this algorithm works, but in the last 10 years no one can show this. Okay, so what is our proof idea is just take their algorithm and kind of use the idea of local visibility containment, but a little bit altered. Just the idea, and then we have to fix some stuff. Okay. So, and in the following, what I will show you is I will hide details, which I don't deem necessary for the main idea, and there are quite a bunch of them. And I already did do this actually, but later I will point out some of those pitfalls. Okay, so let's start why the algorithm of Deshpande fails. Okay, so it fails for this very simple polygon here. So this is here an extension of these two reflex vertices, and consider this point A1. It has this visibility region, and we consider A2, which has this slightly smaller visibility region. A2 went closer to this extension line, and A3 has an even smaller visibility region, and so on and so forth. So we could think of a sequence here of points going closer and closer to the extension line. I can't redraw it, and it would just be invisible, but you could imagine this continuing. And there's a few things you should notice. So as long as none of these AIs is actually on the line, no one can see T. And if you're close enough to T, somehow all of those visibility regions are distinct here. So no two see the same. There's no visibility which dominates all the others. Okay, so this said, let's look now at the point cloud that's generated by Deshpande. It's finite, so don't really care how many points there are, but it's finite. And then by the what I told you just before, there's some small region around T. It's even much smaller than what I drew here, but it exists, which is not seen by any of those. Right? Because if you're on this line, you see T. If you're slightly above the line like this, you're kind of slightly away from T. So there's some small region which is seen by no one. So now what the optimal solution could do, it could just be so that it's very close to this extension and just sees part of this green stuff. So what happens now, that no matter how many points you take around this point X, none of them can see everything that's seen by this point. It might be only tiny, but you see local visibility containment is possible. And this is also why the algorithm of Deshpande fails. And now the hope for the remaining talk is that this can only happen close to the extension line. And so if you're not close to the extension line, you use local visibility containment. If you're close to the extension line, you do something else. You just take one of these reflex vertices. That's fine. Okay, so let's see. If I'm in a bad region, if X is not in a bad region, then the local visibility containment lemma says, the points around the grid, some grid points around X see everything that X sees. So that's it. And I will give a proof sketch later, but let's I want to tell you how to use it. So we get somehow that our grid solution is at most 5 times away from the optimum. How this? So the optimum grid is at most this G, that which I will specify in a minute. G is some subset of the grid, and this is at most 5 opt. So let's see how this works. For each point here, we just take 3 points around it, this small triangle, and then also if you're in a bad region, I just take this point. And now if no point is in 3 bad regions, then I add at most 2 of these points. So G will have size at most 5 opt. So I have to tell you now why should X not be in 3 bad regions. So you could imagine, right, so you have these 3 bad regions and X is in here. But what you see is that these, as I can define these bad regions very, very small, all these extension points have to be very small. And here the integer vertex assumption hits in, and basically it says if these 3 are extremely close, then they must be actually equal. This might sound a little bit surprising at first when you hear it, but think of 2 vertices. If they're close, they must be the same. That is trivial, right? If they're closer than 1, they must be the same. But the same happens here. It's tedious proof, but it's the same idea. And now this would violate our general position, because we said that we don't want to have this to happen. and we're done. Okay, so so now it remains to tell you if X is not in a bad region, why do we have this local containment property? Yeah, here, so let's, okay, if I take 3 or 4, it doesn't really matter, points around, then we have these two cases. Either X sees one of those grid points, then this point sees everything which is in this cone here, because this cone is convex, and this point, yeah, it cannot be blocked by anything in here because it's convex. Yeah. And so now let's say we have this other case that X sees this cone here, and we want that these two vertices also see this cone, these two grid points. Then yeah, then it might happen that it doesn't happen, but it can only happen here in this small region behind. But if this distance close to this grid point is smaller than this distance, then we're done. And morally that's the case, because this distance here should be something, should be our grid width, whereas this distance here is at least 1. Our grid width will be much smaller than 1, and then this should not happen. And then the actual proof is tedious, but the idea is we distinguish two cases. We either look at what is this angle between our X and this closer grid point. If it's smaller than 40, if it's larger than 45 degree, we compare this horizontal distance here. We know this at least 1, this at most 2w. And if it's smaller than 45 degree, then it cannot be too small, because otherwise X would be in a bad region. And then we compare this vertical distance, and as we are not in a bad region, this must be at least 2w, and this here can be at most 2w, because okay, this distance is w. Okay, so this is a proof idea. It's pretty straightforward. Okay, so this finishes my talk, but before I finish, I don't want to let you go away without you thinking we haven't done serious work, right? So to tell you that we did serious work, let me tell you about things that I didn't tell you about. So I told you about that if there's a point, we just take 3 grid points around it. But what about our point is close to an edge, then we have to define them differently. Or even close to a vertex, then we have to take even more points around, and we get worse constants. And for technical reasons, even as a point, if a reflex vertex is fairly far away, so diam to the -1, which is much larger than our grid width, then we also have to include it. So already the grid point definition here gets much more complicated. And then I also didn't tell you how these cones are defined, but this is fairly easy. So just take the visibility region, and then this visibility region decompose into triangles, and you treat each triangle separately. Then there is a nasty thing which we call partial blocking. So maybe these are our 2 grid points which we choose, and then there might be these points blocking the visibility region of those 2, despite the fact that they're not blocking the visibility region of our X. But we can show that this is limited, but it's I mean, it's a 1-page proof. It's kind of lengthy, and because of this, we also have to define our bad regions in a slightly different way. So it's not just anything around the extension, but this region around the extension that is indicated here, and then we have to specify an angle. And because of this limited blocking, we have to talk also about these ambiguous regions, which just are slightly larger. And then we have to show that even if, so it's kind of tricky, but even if X is outside of this bad region, then it's not necessarily true that also this grid points are around the bad region, so we also have to show this. So X being outside this bad region means that these grid points are outside this ambiguous but somehow smaller bad region, which is indicated in green. Also not too complicated. And another thing is So I talked about these cones, but what about just the region very close? What about these triangles here? Very before these reflex vertices, not at the cone far away. So we also have to show that these are covered, especially since part might be blocked. So again, this can be done by somehow distinguishing the case that if this guy is blocked, then either someone blocks it inside here and then this vertex sees everything that he would see, or you're blocked in this triangle and then you know that this point must be closed. That's why we had to include it. And then this point sees the part here. It's another page proof and it's kind of tedious. Yeah, so these were kind of most of the pitfalls, and the difficulty was to put all this stuff together. Yeah, I thank you for your attention. I hope you got the main ideas and the main difficult points. Okay,